Finally, we're ready to compare the three designs that we came up with and see how their behaviors are different, see how the input efforts are different. So I'll do this a little bit differently than I've done it before. I'll use some new features in MATLAB, but there's alternate ways we can do it as well. I have here the three root locus transfer functions that we already came up with for our three controllers. That's the GRL 1, 2, and 3 in 81, 82, 83. So those are right from the slides. I also want to compare this with the PD controller that we came up with in the last lecture. So I have its root locus as well. I'll just refresh what that was. So the root locus transfer function was s plus 4 over s squared plus 2s. And that was based on finding a zero of -4. Now I'm going to make my closed loop transfer functions. I could do this entirely in Simulink, but we already have the closed loop transfer functions from the slides, so I'll just recreate them here and do this all using the step. I'm going to get the same results because it's doing a numerical solution either way. This is just an alternate way to do it, but if you wanted to just run through the Simulink multiple times and collect all those results, that would work as well. So I know I can use this new feedback feature. And if I look in the documentation for how that works, this is going to take two transfer functions and give me the feedback control. Now here I have sys1. That is going to be really my complete controller and plant. So you're going to see I'm going to put in my gain and the controller and the plant, or it's really the same as the gain times the G prime. And then sys2, that's if it's going through a sensor, which in this case we don't have, we're not accounting for a sensor there. So I'm just going to put in the 1 as my system 2. So again, we don't have to use feedback, but we're going to see we get the same transfer functions as if we put it in from what we have on the slides. All right, so for example, for the, I'll actually start with this G1 here. So I'm putting in the GRL1, the root locus for our first design. So again, here it is all in descending powers of s. We found for our first design we needed a gain of 8. And if we see what sys2 is, again, we do have to put something there. It's just 1, but as a transfer function. So when I do this calculation, I get G1, which is going to be my closed loop transfer function for the first design, is it's just expanded out here, descending powers of s, the same thing I have from the slides. So revisiting the slide quickly, we already have that closed loop transfer function algebraically. It's identical. It's just didn't eliminate the roots and the zeros like we did algebraically. So again, we should have no zeros and then the two dominant poles only. When we look here, it is a little bit expanded, but it does turn out to be the same thing. If we do a roots on our numerator, 8 and 16, it's -2, but if we do the same thing for the denominator, we're going to have a -2 that's going to cancel out. So that bottom one, -2, that cancels, and that's why we do get the exact same results. It's just not as compact as what we had before. So I'm entering in the closed loop transfer functions for our three designs in 86 through 88, and the closed loop transfer function that we had for our PD controller in the previous lecture. So we already saw this in action. We already know how it works. We have the dominant poles, and then we have that extra 0 at -4 that impacted our response. So we're going to see them all at the same time. All right, so in my figure, I'm going to give each of them that 5-unit step input and plot what their response is. We're also going to see a Bode plot, but we'll save that for a moment. So I'm going to run this section and see all 4 controllers at the same time. We see that the blue is going to be the performance of the PD controller. So that's what we had from the last lecture over here. And then we can see what do our compensators look like. So our first design is in black. We see that it is, again, performing more like the expected baseline function because of those that root and that pole canceling each other out. We see that it has the longer peak time but a lower max overshoot compared to the PD controller. It's how we expected our system to behave. We have our second controller design, and we see it has a greater maximum overshoot and a lower peak time, and that's due to that extra 0 and that extra pole that was in our closed loop transfer function. And then we have kind of the odd one here, our third design. This is where the extra 0 and the extra pole were actually to the right of the real part of our dominant poles. And we see this odd behavior where we don't have an overshoot in it, and we don't have a peak time. So probably these three designs would be ones we might consider for our final controller, the PD, or one of these two compensators. Now, if we compare just those metrics in table form, we can see a little bit more clearly what's happening. So again, an ideal second order system with no extra zeros, extra poles, with its poles at -2 plus or minus 2j, we know how to compute the overshoot and the peak time, and we see they match almost exactly the first design lead compensator. Because again, it eliminated one of our open loop poles by our design. So it performs pretty much exactly like we expected it to. The PD controller with that extra 0, like I just said, higher overshoot and higher peak time, and similar with our second design of the lead compensator, we have an even higher overshoot, and we have a less of a peak time there. And then the third one didn't have the overshoot at all. Now, we only looked at 3 choices of really pairs of zeros and poles for the lead compensator that we could have had, but there's an infinite number of pairs that we could have selected from. So here, let's just look at, here's a graph of if we choose a 0, what the corresponding pole would be that would still satisfy that the dominant poles were located at -2 plus or minus 2j. So if we see here, for a very small value of a 0, our pole choice is going to be 2 already. And as we increase the value of the 0, the pole choice is also going to increase. What we actually see for this particular system and for this particular pole, there's no 0 we can choose where it's actually going to be greater than the pole. So in this case, we could only choose lead compensators that are going to put the dominant poles where we want them. We can't get a lag compensator because we can't get a 0 that's actually greater than the pole that also satisfies that the total angle is 180 degrees when our dominant poles are at -2 plus or minus 2j. That's not always the case. It's particular to this pole selection and this system. But what we see happening is as we start to increase that 0 all the way up to 3, our pole choice goes up to 8. If we kept increasing it to 4, etc., our pole is going to get even larger. As a general rule of thumb, the further left our zeros and poles are in the controller, the more effort it's going to take, the higher peak effort definitely it's going to take for our controller to work properly. So I would say for this particular system, if we chose the dominant poles at -2 plus or minus 2j for a particular overshoot, a particular peak time, of the 4 controllers we're comparing right now, I would say that Compensator 1, the first design, would be the best one. It almost perfectly matches the desired peak time and max overshoot that we had from our original design. But the compensators, it does perform better than the 1 PD controller we looked at. However, the compensators are good when the desired output of our system is not a step function, but when it is periodic. So just briefly, I want to compare the Bode plots of these 4 systems. All right, so if we see the PD controller in blue here, we see that, let's look at the magnitude in decibels first. Its roll-off, its attenuation of these high-frequency signals is much different than the lead compensators, the 3 lead compensators that we came up with. And also its phase is a lot different. It goes to -90 degrees, whereas all the compensators go into anti-phase, -180 at high frequencies. But the high-frequency performance of the lead compensators of the high frequencies looks kind of similar to each other, and the angle it goes off at is much different than the angle for the proportional differential controller. Now, if we did have a lag compensator, we would see another more differences in the magnitude and the phase in the Bode diagram, but keep in mind for future reference that lead and lag compensators, their frequency responses are sometimes a desirable aspect when we are going through their design. So as a final wrap up here, the best compensator, the one that was closest to our desired performance, was our first lead compensator design with a 0 at 2 and a pole at 4. And we saw in this case that that 0 that we chose canceled a pole in the open loop system. And that's an attractive feature. Our design 3 had a 0 and actually a pole both to the right of the dominant closed loop poles, and that definitely affected the performance. We didn't see it have overshoots like we would expect, like a second order system, but in fact it's not a second order system. It had 3 poles and 1 0. We couldn't make a lag compensator for this particular desired pole and this open loop system. That's not universally going to be the case. And we saw that the frequency responses differed when we used the PD controller and compared it to the 3 designs for our lead compensator controllers.